Hey folks, welcome to the third lecture of Full Stack Deep Learning 2022. I'm Charles Fry. Today I'll be talking about troubleshooting and testing. High level outline of what we're going to cover today. We'll talk about testing software in general and the sort of standard tools and practices that you can use to de-risk shipping software quickly. Then we'll move on to special considerations for testing machine learning systems, the specific techniques and approaches that work best there. And then lastly, we'll go through what you do when your models are failing their tests, how you troubleshoot your model. First, let's cover concepts for testing software. So the general approach that we're going to take is that tests are going to help us ship faster with fewer bugs, but they aren't going to catch all of our bugs. And that means though we're going to use testing tools, we aren't going to try and achieve 100% coverage. Similarly, we're going to use linting tools to try and improve the development experience, but leave escape valves rather than pedantically just following our style guides. Lastly, we'll talk about tools for automating these workflows. So first, why are we testing at all? Tests can help us ship faster, even if they aren't catching all bugs before they go into production. So as a reminder, what even are tests? Tests are code we write that's designed to fail in an intelligible way when our other code has bugs. So for example, this little test for the text recognizer from the full stack deep learning code base checks whether the output of the text recognizer on a particular input is the same as what was expected and raises an error if it's not. And these kinds of tests can help catch some bugs before they're merged into main or shipped into production, but they can't catch all bugs. And one reason why is that test suites in the tools we're using are not certificates of correctness. In some formal systems, tests like those can actually be used to prove that code is correct. But we aren't working in one of those systems like Agda, the theorem proving language, or Idris 2. We're writing in Python. And so really it's a loosey-goosey language and all bets are off in terms of code correctness. So if test suites aren't like certificates of correctness, then what are they like? I like this framing from Nelson Elhaga, who's at Anthropic AI, who says that we should think of test suites as being more like classifiers and sort of bring our intuition from working with classification algorithms and machine learning. So the classification problem is, does this commit have a bug or is it okay? And what our classifier outputs is that the tests pass or the tests failed. So our tests are our classifier of code. And so we should think of that as a prediction of whether there's a bug. This kind of frame shift suggests a different way of designing our test suites. When we design classifiers, we know that we need to trade off detection and false alarms. Lots of people are thinking about detection when they're designing their test suites. They're trying to make sure that they will catch all of the possible bugs. But in doing so, we can inadvertently introduce false alarms. So the classic signature of a false alarm is a failed test that's followed by a commit that fixes the test rather than the code. So that's an example from the full stack deep learning code base. So in order to avoid introducing too many false alarms, it's useful to ask yourself two questions before adding a test. So the first question is, which real bugs will this test catch? What are some actual ways that the world might change around this code, or that somebody might introduce a change to some part of the code base that this test will catch? Once you've listed a couple of those, then ask yourself, what are some false alarms that this test might raise? What are some ways that the world around the test or the code could change that's still valid and good code, but now this test will fail? And if you can think of more examples for the latter case than the former, then maybe you should reconsider whether you really need this test. One caveat to this, in some settings, it actually is really important that you have a super high degree of confidence in the correctness of your code. So this screenshot is from a deep learning diagnostic tool for cardiac ultrasounds by Caption Health that I worked on in an internship. In that project, we had a ton of concern about the correctness of the model, the confidence people had in the model, and regulators expected to see that kind of information. So there's other cases where this level of correctness is needed. Self-driving cars is one example. You also see this in banking and finance. There are a couple of patterns that immediately arise here. One is the presence of regulators and more generally high stakes. If you're operating in a high stakes situation where errors have consequences for people's lives and livelihoods, even if it's not regulated yet, it might be regulated soon. And in particular, these are also all examples of those autonomous systems, that class of low feasibility, high impact machine learning project that we talked about in the first lecture. This is one of the reasons for their low feasibility, is because correctness becomes really important for these kinds of autonomous systems. So what does this mindset mean for how we approach testing and quality assurance for our code? It means that we're going to use testing tools, but we don't want to aim for complete coverage of our code. So in terms of tools, pytest is the standard tool for testing Python code. It is a very Pythonic implementation and interface, and it has also a ton of powerful features like marks for creating separate suites of tests, sharing resources across tests, and running tests in a variety of parameterized variations. In addition to writing the kinds of separate test suites that are standard in lots of languages, in Python, there's a nice built-in tool called doctests for testing the code inside of our doc strings. And this helps make sure that our doc strings don't get out of sync with our code, which builds trust in the content of those doc strings and makes them easier to maintain. Doc tests are really nice, but there are some limits. They're framed around code snippets that could be run in a terminal. And so they can only display what can be easily displayed in a terminal. Notebooks, on the other hand, can display things like rich media, charts, images, and web pages, also interleaved with code execution and text. So for example, with our data processing code, we have some notebooks that have charts and images in them that explain choices in that data processing. Trouble is, notebooks are hard to test. We use a cheap and dirty solution. We make sure that our notebooks run end to end. Then we add some assert statements, and we use NB format to run the notebooks and flag when they fail. So once you start adding lots of different types of tests, and as your code base grows, you're going to want to have tooling for recording what kind of code is actually being checked or covered by the tests. And typically, this is done in terms of lines of code, but some tools can be a little bit more finer grained. The tool that we recommend for this is called codecov. It generates a lot of really nice visualizations that you can use to drill down or get a high level overview of the current state of your testing. So this is a great tool for helping you understand your testing and its state. It can be incorporated into your testing, effectively saying, I'm going to reject commits not only where tests fail, but also where test coverage goes down below some value or by a certain amount. But we actually recommend against that. Personal experience, interviews, and even some published research suggests that only a small fraction of the tests that you write are going to generate the majority of your value. And so the right tactic, engineering-wise, is to expend the limited engineering effort that we have on the highest impact tests and making sure those are super high quality. But if you set a coverage target, then you're instead going to write tests in order to meet that coverage target, regardless of their quality. So you end up spending more effort both to write the tests and then to maintain and deal with their low quality. In addition to checking that our code is correct, we're going to also want to check that our code is clean with linting tools. But with the caveat that we always want to make sure that there are escape valves from these tools. When we say the code is clean, what we mean is that it's of a uniform style and of a standard style. So uniform style helps avoid spending engineering time on arguments over style in pull requests and code review. It also helps improve the utility of our version control system by cutting down on unnecessary noisy components of diffs and reducing their size. Both of these things will make it easier for humans to visually parse the diffs in our version control system and make it easier to build automation around them. And then we also generally want to adopt a standard style in whatever community it is that we are writing our code. If you're an open source repository, this is going to make it easier to accept contributions. And even if you're working on a closed source team, if your new team members are familiar with this style that's standard in the community, they'll be faster to onboard. One aspect of consistent style is consistent formatting of code with things like whitespace. The standard tool for that in Python is the black Python formatter. It's a very opinionated tool, but it has a fairly narrow scope in terms of style. It focuses on things that can be fully automated. So you can see it not only detects deviations from style, but also implements the fix. So that's really nice, integrated into your editor, integrated into automated workflows, and avoid engineers having to implement these things themselves. For non-automatable aspects of style, the tool we recommend is Flake 8. Non-automatable aspects of style are things like missing doc strings. We don't have good enough automation tools to reliably generate doc strings for code automatically. So these are going to require engineers to intervene in order to fix them. One of the best things about Flake 8 is that it comes with tons of extensions and plugins. So you can check things like docstring style and completeness, like type hinting, and even for security issues and common bugs, all via Flake 8 extensions. So those cover your Python code. ML code bases often have both Python code and shell scripts in them. And shell scripts are really powerful, but they also have a lot of sharp edges. So shellcheck knows about all these kinds of weird behaviors of bash that often cause errors and issues that aren't immediately obvious. And it also provides explanations for why it's raising a warning or an error. It's a very fast to run tool, so you can incorporate it into your editor. And because it includes explanations, you can often resolve the issue without having to go to Google or Stack Overflow and switch contexts out of your editing environment. So these tools are great and a uniform style is important, but really pedantically enforcing style can be self-defeating. So I searched for the word placate on GitHub and found over 100,000 commits mentioning placating these kinds of automated style enforcement tools. And all of these commits sort of drip frustration from engineers who are spending time on this that they wish that they were not. So to avoid frustration with code style and linting, we recommend filtering your rules down to the minimal style that achieves the goals that we set of sticking with standards and of avoiding arguments and of keeping version control history clean. Another suggestion is to have an opt-in rather than an opt-out application of rules. So by default, many of these rules may not be applied to all files in the code base, but you can opt in and add a particular rule to a particular file. And then you can sort of grow this coverage over time and avoid these kinds of frustrations. This is especially important for applying these kinds of style recommendations to existing code bases, which may have thousands of lines of code that need to be fixed. And in order to make best use of these testing and linting practices, you're going to want to embrace automation as much as possible in your development workflows. For the things we talked about already with testing and linting, you're going to want to automate these and connect them to your cloud version control system and run these tasks in the cloud or otherwise outside of development environments. So connecting to version control state reduces friction when trying to reproduce or understand errors, and running things outside of developer environments means that you can run these tests in parallel to other development work. So you can kick off tests that might take 10 or 20 minutes and spend that time responding to Slack messages or moving on to other work. One of the best places to learn about best practices for automation are popular open source repos. So I checked out PyTorch's GitHub repository and found that they had tons and tons of automated workflows built into the repository. They also followed what I think are some really nice practices, like they had some workflows that are automatically running on every push and pull. And these are mostly code-related tasks that run for less than 10 minutes. So that's things like linting and maybe some of the quicker tests. Other tasks that aren't directly code related, but maybe do things like check dependencies, and any code related tasks that take more than 10 minutes to run are run on a schedule. So we can see that, for example, closing stale pull requests is done on a schedule because it's not code related. PyTorch also runs a periodic suite of tests that takes hours to run. You don't want to run that every time that you push or pull. So the tool that they use and that we recommend is GitHub Actions. This ties your automation entirely directly to your version control system, and that has tons of benefits. Also, GitHub Actions is really powerful. It's really flexible. There's a generous free tier. It's performant. And on top of all of this, it's really easy to use. It's got really great documentation. Configuring GitHub Actions is done just using a YAML file. And because of all of these features, it's been embraced by the open source community, which has contributed lots and lots of GitHub Actions that maybe already automate the workflow that you're interested in. That's why we recommend GitHub Actions. There are other options, precommit.ci, CircleCI, and Jenkins. All great choices, all automation tools that I've seen work, but GitHub Actions seems to have won hearts and minds in the open source community in the last couple of years. So that makes sure that these tests and lints are being run in code before it's shipped or before it's merged into main. But part of our goal was to keep our version control history as clean as possible. So we want to be able to run these locally as well and before committing. And so for that, we recommend a tool called Precommit, which can run all kinds of different tools and automations automatically before commits. So it's extremely flexible and can run lots of stuff. You will want to keep the total runtime to just a few seconds, or you'll discourage engineers from committing, which can lead to work getting lost. Pre-commit's super easy to run locally, in part because it separates out the environment for these linting tools from the rest of the development environment, which avoids a bunch of really annoying tooling and system administration headaches. They're also super easy to automate with GitHub Actions. Automation to ensure the quality and integrity of our software is a huge productivity enhancer that's broader than just CI/CD, which is how you might hear tools like GitHub Actions referred to. Automation helps you avoid context switching. If a task is being run fully automatically, then you don't have to switch contexts and remember the command line arguments that you need in order to run your tool. It surfaces issues more quickly than if these things were being run manually. It's a huge force multiplier for small teams that can't just throw engineer hours at problems, and it's better documented than manual processes. The script or artifact that you're using to automate a process serves as documentation for how a process is done if somebody wants to do it manually. The one caveat is that fully embracing automation requires really knowing your tools well. Knowing Docker well enough to use it is not the same as knowing Docker well enough to automate it, and bad automation, like bad tests, can take more time away than it saves. So organizationally, that actually makes automation a really good task for senior engineers who have knowledge of these tools, have ownership over code, and can make these kinds of decisions around automation, perhaps with junior engineer mentees to actually write the implementations. So in summary, automate tasks with GitHub Actions to reduce friction in development and move more quickly. Use the standard Python toolkit for testing and cleaning your projects, and choose in that toolkit the testing and linting practices with the 80-20 principle for tests, with shipping velocity, and with usability and developer experience in mind. Now that we've covered general ideas for testing software systems, let's talk about the specifics that we need for testing machine learning systems. The key point in this section is that testing ML is difficult, but if we adapt ML-specific coding practices and focus on low-hanging fruit to start, then we can test our ML code. And then additionally, testing machine learning means testing in production, but testing in production doesn't mean that you can just release bad code and let God sort it out. So why is testing machine learning hard? So software engineering is where a lot of testing practices have been developed. And in software engineering, we compile source code into programs. So we write source code, and a compiler turns that into a program that can take inputs and return outputs. In machine learning, training compiles, in a sense, data into a model. And all of these components are harder to test in the machine learning case than in the software engineering case. Data is heavier and more inscrutable than source code. Training is more complex, less well-defined, and less mature than compilation. And models have worse tools for debugging and inspection than compiled programs. So this means that ML is the Dark Souls of software testing. It's a notoriously difficult video game. But just because something is difficult doesn't mean that it's impossible. In the latest Souls game, Elden Ring, a player named Let Me Solo Her defeated one of the hardest bosses in the game wearing nothing but a jar on their head. If testing machine learning code is the Dark Souls of software testing, then with practice and with the right techniques, you can become the Let Me Solo Her of software testing. And so in our recommendations in this section, we're going to focus mostly on what are sometimes called smoke tests, which let you know when something is on fire and help you resolve that issue. So these tests are easy to implement, but they are still very effective. So they're among the 20% of tests that get us 80% of the value. For data, the kind of smoke testing we recommend is expectation testing. So we test our data by checking basic properties. We express our expectations about the data, which might be things like, there are no nulls in this column. The completion date is after the start date. And so with these, you're going to want to start small, checking only a few properties, and grow them slowly, and only test things that are worth raising alarms over, worth sending people notifications, worth bringing people in to try and resolve them. So you might be tempted to say, oh, these are human heights. They should be between 4 and 8 feet. But actually, there are people between the heights of 2 and 10 feet. So loosening these expectations to avoid false positives is an important way to make them more useful. So you can even say that height should be not negative and less than 30 feet. And that will catch somebody maybe accidentally entering a height in inches, but it doesn't express strong expectations about the statistical distribution of heights. You could try and build something for expectation testing with a tool like pytest, but there's enough specifics and there's good enough tools that it's worth reaching for something else. So the tool we recommend is Great Expectations, in part because Great Expectation automatically generates documentation for your data and quality reports and has built-in logging and alerting designed for expectation testing. So we are going to go through this in the lab. We'll go through a lot of the other tools that we've talked about in the lab this week. So if you want to check out Great Expectations, we recommend the Made with ML tutorial on Great Expectations by Gogu Mohandas. Loose expectation testing is a great start for testing your data pipeline. What do you do as you move forward from that? The number one recommendation that I have is to stay as close to your data as possible. So from top to bottom, we have data annotation setups going from furthest away from the model development team to closest. One common pattern is that there's some benchmark data set with annotations that you're using, which is super common in academia, or there's an external annotation team, which is very common in industry. And in that case, a lot of the detailed information about the data that you can learn by looking at it and using it yourself are going to be internalized into the organization. So one way that sometimes does get internalized is that at the start of the project, some data will get annotated ad hoc by model developers, especially if you're not using some external benchmark data set or you don't yet have budget for an external annotation team. And that's an improvement, but if the model developers who are around at the start of the project move on, and as more developers get onboarded, that knowledge is diluted. Better than that is an internal annotation team that has regular information flow, whether that's stand-ups and syncs or exchange of documentation. That information flows to the model developers. But probably the best practice, and one that I saw recommended by Shreya Shankar on Twitter, is to have a regular on-call rotation where model developers annotate data themselves, ideally fresh data, so that all members of the team who are developing models know about the data and develop intuition and expertise in the data. For testing our training code, we're going to use memorization testing. So memorization is the simplest form of learning. Deep neural networks are very good at memorizing data. And so checking whether your model can memorize a very small fraction of the full data set is a great smoke test for training. And if a model can't memorize, then something is clearly very wrong. Only really gross issues with training are going to show up with this test. So your gradients aren't being calculated correctly, you have a numerical issue, your labels have been shuffled, and subtle bugs in your model or your data are not going to show up in this. But you can improve the coverage of this test by including the runtime in the test, because regressions there can reveal bugs that just checking whether you can eventually memorize a small data set wouldn't reveal. So if you're including the wall time, that can catch performance regressions, but also if you're including the number of steps or epochs required to hit some criterion value of the loss, then you can catch some of these small issues that make learning harder, but not impossible. There's a nice feature of PyTorch Lightning overfit batches that can quickly implement this memorization test. And if you design them correctly, you can incorporate these tests into end-to-end model deployment testing to check to make sure that the data that the model memorized in training is also something it can correctly respond to in production. With these memorization tests, you're going to want to tune them to run quickly so that you can run them as often as possible. If you can get them to under 10 minutes, you might run them on every pull request or on every push. So this is something that we worked on in updating the course for 2022. So the simplest way to speed these jobs up is to simply buy faster machines. But if you're already on the fastest machines possible, or you don't have budget, then you can start by reducing the size of the data set that the model is memorizing down to the batch size that you want to use in training. Once you reduce the batch size below what's in training, you're starting to step further and further away from the training process that you're trying to test. And so going down this list, we're getting further and further from the thing that we're actually testing, but allowing our test to run more quickly. The next step that can really speed up a memorization test is to turn off regularization, which is meant to reduce overfitting, and memorization is a form of overfitting. So that means turning off dropout, turning off augmentation. You can also reduce the model size without reducing the architecture. So reduce the number of layers, reduce the widths of layers while keeping all of those components in place. And if that's not enough, you can remove some of the most expensive components. And in the end, you should end up with a tier of memorization tests, which are more or less close to how you actually train models in production that you can run on different timescales. One recommendation you'll see moving forward and trying to move past just smoke testing by checking for memorization is to rerun old training jobs with new code. So this is never something that you're going to be able to run on every push. Probably not nightly either if you're looking at training jobs that run for multiple days. And the fact that this takes a long time to run is one of the reasons why it's going to be really expensive, no matter how you do it. For example, if you're going to be doing this with Circle CI, you'll need GPU runners to execute your training jobs, but those are only available in the enterprise level plan, which is $24,000 a year at a bare minimum. I've seen some very large bills for running GPUs in Circle CI. GitHub Actions, on the other hand, does not have GPU runners available, so you'll need to host them yourself, though it is on the roadmap to add GPU runners to GitHub Actions. And that means that you're probably going to maybe double your training spend. Maybe you're adding an extra machine to rerun your training jobs, or maybe you're adding to your cloud budget to pay for more cloud machines to run these jobs. And all this expenditure here is only on testing code. It doesn't have any connection to the actual models that we're trying to ship. The best thing to do is to test training by regularly running training with new data that's coming in from production. This is still going to be expensive because you're going to be running more training than you were previously, but now that training spend is going to model development, not code testing. So it's easier to justify. Having this set up requires the data flywheel that we talked about in lecture 1. And that requires production monitoring, tooling, and all kinds of other things that we'll talk about in the monitoring and continual learning lecture. Lastly, for testing our models, we're going to adapt regression testing. At a very base level, models are effectively functions. So we can test them like functions. They take in inputs, they produce outputs. We can write down what those outputs should be for specific inputs and then test them. This is easiest for classification and other tasks with simple output. If you have really complex output, like for example, our text recognizer that returns tests, then these tests can often become really flaky and hard to maintain. But even for those kinds of outputs, you can use these tests to check for differences between how the model is behaving in training and how it's behaving in production. The better approach that's still relatively straightforward is to use the values of the loss and your metrics to help build documented regression test suites out of your data, out of the data you're using in training and the data you see in production. The framing that I like to bring to this comes from test-driven development. So test-driven development is a paradigm for testing that says first you write the test, and that test fails because you haven't written any of the code that it's testing. And then you write code until you pass the test. This is straightforward to incorporate into testing our models because in some sense, we're already doing it. Think of the loss as like a fuzzy test signal. Rather than simply failing or not failing, the loss tells us how badly a test was failed. So how badly did we miss the expected output on this particular input? And so just like in test-driven development, that's a test that's written before that code writing process. And during training, our model is changing, and it changes in order to do better on the tests that we're providing. And the model stops changing once it passes the test. So in some sense, gradient descent is already test-driven development. And maybe that is an explanation for the Carpathy quote that gradient descent writes better code than me. But just because gradient descent is test-driven development doesn't mean that we're done testing our models. Because what's missing here is that the loss and other metrics are telling us that we're failing, but they aren't giving us actionable insights or a way to resolve that failure. The simplest and most generic example is to find data points with the highest loss in your validation and test set or coming from production and put them in a suite labeled hard. But note that the problem isn't always going to be with the model. Searching for high loss examples does reveal issues about what your model is learning, but it also reveals issues in your data like bad labels. So this doesn't just test models, it also tests data. And then we want to aggregate individual failures that we observe into named suites of specific types of failure. So this is an example from a self-driving car task of detecting pedestrians, cases where pedestrians were not detected. It's much easier to incorporate this into your workflows if you already have a connection between your model development team and your annotation team. Reviewing these examples here, we can see that what seems to be the same type of failure is occurring more than once. In 2 examples, there's a pedestrian who's not visible because they're covered by shadows. In 2 examples, there are reflections off of the windshield that are making it harder to see the pedestrian. And then some of the examples come from night scenes. So we can collect these up, create a data set with that label, and treat these as test suites to drive model development decisions. And so this is kind of like the machine learning version of a type of testing called regression testing, where you take bugs that you've observed in production and add them to your test suite to make sure that they don't come up again. So the process that I described is very manual, but there's some hope that this process might be automated in the near future. A recent paper described a method called Domino that uses much, much larger cross-modal embedding models, so foundation models, to understand what kinds of errors a smaller model, like a specific model designed just to detect birds or pedestrians, what kinds of mistakes is it making on images. As your models get more mature and you understand their behavior and the data that they're operating on better, you can start to test more features of your models. So for more ways to test models with an emphasis on NLP, see the checklist paper that talks about different ways to do behavioral testing of models. In addition to testing data, training, and models in our development environment, we're also going to want to test in production. And the reason why is that production environments differ from development environments. This is something that is true for complex software systems outside of machine learning. So Charity Majors of Honeycomb has been a big proponent of testing in production on these grounds. And this is especially true for machine learning models because data is an important component of both the production and the development environments. And it's very difficult to ensure that those two things are close to each other. And so the solution in this case is to run our tests in production. But testing in production doesn't mean only testing in production. Testing in production means monitoring production for errors and fixing them quickly. As Chip Wynn, the author of Designing Machine Learning Systems, pointed out, this means building infrastructure and tooling so that errors in production are quickly fixed. Doing this safely and effectively and ergonomically requires tooling to monitor production, and a lot of that tooling is fairly new, especially tooling that can handle the particular type of production monitoring that we need in machine learning. We'll cover it along with monitoring and continual learning in that lecture. So in summary, we recommend focusing on some of the low-hanging fruit when testing ML and sticking to tests that can alert you to when the system is on fire. So that means expectation tests of simple properties of data, memorization tests for training, and data-based regression tests for models. But what about as your code base and your team matures? One really nice rubric for organizing the testing of a really mature ML code base is the ML test score. So the ML test score came out of Google research, and it's this really strict rubric for ML test quality. So it includes tests for data, models, training infrastructure, and production monitoring. And it overlaps with, but goes beyond some of the recommendations that we've given already. Maintaining and automating all of these tests is really expensive, but it can be worth it for a really high stakes or large scale machine learning system. So we didn't use the ML test score to design the text recognizer code base, but we can check what we implemented against it. Some of the recommendations in the machine learning test score didn't end up being relevant for our model. For example, some of the data tests are organized around tabular data for traditional machine learning rather than for deep learning. But there's still lots of really great suggestions in the ML test score. So you might be surprised to see we're only hitting a few of these criteria in each category. But that's a function of how strict this testing rubric is. So they also provide some data on how teams doing ML at Google did on this rubric. And if we compare ourselves to that standard, the text recognizer is about in the middle, which is not so bad for a team not working with Google scale resources. Tests alert us to the presence of bugs, but in order to resolve them, we'll need to do some troubleshooting. And one of the components of the machine learning pipeline that's going to need the most troubleshooting and which is going to require very specialized approaches is troubleshooting models. So the key idea in this section is to take a 3-step approach to troubleshooting your model. First, make it run by avoiding the common kinds of errors that can cause crashes, shape issues, out-of-memory errors, and numerical problems. Then, make your model fast by profiling it and removing any bottlenecks. Then lastly, make the model right. Improve its performance on test metrics by scaling out the model and the data and sticking with proven architectures. First, how do we make a model run? Luckily, this step is actually relatively easy in that only a small portion of bugs in machine learning cause the kind of loud failure that we're tackling here. So there's shape errors, out-of-memory errors, and numerical errors. Shape errors occur when the shapes of tensors don't match the shapes expected by the operations applied to them. So while you're writing your PyTorch code, it's a good idea to keep notes on what you expect the shapes of your tensors to be, to annotate those in the code as we do in the full stack deep learning code base, and to even step through this code in a debugger, checking the shapes as you go. Another one of the most common errors in deep learning is out of memory when you try and push a tensor to the GPU that's too large to fit on it. It's something of a rite of passage for deep learning engineering. Luckily, PyTorch Lightning has a bunch of really nice tools built into this. First, make sure you're using the lowest precision that your training can tolerate. A good default is half precision floats or 16-bit floats. A common culprit is that you're trying to run your model on too much data at once, on too large of a batch. So you can use the auto scale batch size feature in PyTorch Lightning to pick a batch size that uses as much GPU memory as you have, but no more. And if that batch size is too small to get you stable gradients that can be used for training, you can use gradient accumulation across batches, also easily within Lightning, to get the same gradients that you would have gotten if you'd calculated on a much larger batch. If none of those work and you're already operating on GPUs with the maximum amount of RAM, then you'll have to look into manual techniques like tensor parallelism and gradient checkpointing. Another cause of crashes for machine learning models is numerical errors when tensors end up with nans or infinite values in them. Most commonly, these numerical issues appear first in the gradient. The gradients explode or shrink to zero, and then the values of parameters or activations become infinite or nan. So you can observe some of these gradient spikes occurring in some of the experiments for the DALL-E Mini project that have been publicly posted. PyTorch Lightning comes with a nice tool for tracking gradient norms and logging them so that you can see them and correlate them with the appearance of nans and infinities and crashes in your training. A nice debugging step to check what the cause might be, whether the cause is due to precision issues or due to a more fundamental numerical issue, is to switch to double precision floats, the default floating point size in Python, 64-bit floats, and see if that causes these issues to go away. If it doesn't, then that means that there's some kind of issue with your numerical code, and you'll want to find a numerically stable implementation to base your work off of, or apply error analysis techniques. And one of the most common causes of these kinds of numerical errors are the normalization layers like batch norm and layer norm. That's what's involved in these gradient spikes in DALL-E Mini. So you'll want to make sure to check carefully that you're using normalization in the way that's been found to work for the types of data and architectures that you're using. Once your model can actually run end to end and calculate gradients correctly, the next step is to make it go fast. This could be tricky because the performance of deep neural network training code is very counterintuitive. For example, with typical hyperparameter choices, transformer layers spend more time on the plain old MLP component than they do on the intention component. And as we saw in lecture 2, for popular optimizers, just keeping track of the optimizer state actually uses more GPU memory than any of the other things you might expect would take up that memory, like model parameters or data. And then furthermore, without careful parallelization, what seem like fairly trivial components like loading data can end up dwarfing what would seem like the actual performance bottlenecks, like the forwards and backwards passes and parameter updates. The only solution here is to kind of roll up your sleeves and get your hands dirty and actually profile your code. So we'll see this in the lab. But the good news is that you can often find relatively low-hanging fruit to speed up training, like making changes just in the regular Python code and not in any component of the model. And lastly, once you've got a model that can run and that runs quickly, it's time to make the model correct by reducing its loss on test or production data. The normal recommendation for software engineering is make it run, make it write, make it fast. So why is make it write last in this case? And the reason why is that machine learning models are always wrong. Production performance is never perfect. And if we think of non-zero loss as a partial test failure for our models, then our tests are always at least partially failing. So it's never really possible to truly make it right. And then the other reason that we want to put performance first is that you can kind of solve all your problems with model correctness with scale. So if your model is overfitting to the training data and your production loss is way higher, then you can scale up your data. If your model is underfitting and you can't get the training loss to go down as much as you'd like, then scale up your model. If you have distribution shift, which means that your training and validation loss are both low, but your production or test loss is really high, then just scale up both. Folks at OpenAI and elsewhere have done work demonstrating that the performance benefits from scale can be very rigorously measured and predicted across compute budget, dataset size, and parameter count. Generating these kinds of scaling law charts is an important component of OpenAI's workflows for deciding how to build models and how to run training. But scaling costs money. So what do you do if you can't afford the level of scale required to reach the performance that you want? In that case, you're going to want to fine tune or make use of a model trained at scale for your tasks. This is something we'll talk about in the Building on Foundation Models lecture. All the other advice around addressing overfitting, addressing underfitting, resolving distribution shift is going to be model and task specific, and it's going to be hard to know what is going to work without trying it. So this is just a selection of some of the advice I've seen given or been given about improving model performance, and they're mutually exclusive in many cases because they're so tied to the particular task and model and data that they're being applied to. So the easiest way to resolve this is to stick as close as possible to working architectures and hyperparameter choices that you can get from places like the Hugging Face Hub or Papers with Code. And in fact, this is really how these hyperparameter choices and architectures arise. It's via a slow evolutionary process of people building on techniques and hyperparameter choices that work rather than people designing things entirely from scratch. So that brings us to the end of the troubleshooting and testing lecture. We covered the general approach to testing software, both tools and practices that you can use to ship more safely, more quickly. Then we covered the specific things that you need in order to test ML systems, data sets, training procedures, and models, both the most basic tests that you should implement at the beginning, and then how to grow those into more sophisticated, more robust tests. And then lastly, we considered the workflows and techniques that you need to troubleshoot model performance. So we'll see more on all of these topics in the lab for this week. If you'd like to learn more about any of these topics, check out the slides online for a list of recommended Twitter follows, project templates, and medium to long form text resources to learn more about troubleshooting and testing. That's all for this lecture. Thanks for listening and happy testing.